Hello everyone and welcome to this talk. I really hope you and your family are doing great during this pandemic situation. In this talk, I'm going to talk about a rank attack against a multivariate scheme called extension field cancellation. This, were, this was a joint work with Daniel Smith while I was visiting him in the University of Louisville. I'm gonna start this talk by describing a little bit very quickly what extension field cancellation is, and then what's the rank property that allows us to perform a key recovery attack, and then I'm gonna show you what are the key steps in that key recovery attack. Then I'm gonna show you the details of one method that is gonna be used sometimes during the attack, but it is like a really nice technique by itself. I'm gonna show you later what what the deal with that. And finally, we're gonna discuss a little bit the complexity of this attack. Okay, extension field cancellation was an encryption scheme proposed by Szepieniec, Bing, and Preneel. It was proposed in 2010, and it was like one of the most promising schemes based on multivariate cryptography at that time. In this talk, we're going to use two fields, a field E, which is an extension field, and a field FQ with Q element, which is we are going to call our base field or small field. Uh, the extension the extension field is a degree n extension, and here we're going to denote like by x this vector of variables, the vector of n variables. Uh, for two given matrices A and B, we're going to define two maps, two matrices which contain linear form in the x variables, and the coefficient of such a linear forms are going to depend on these two matrices A and B. The coefficient of alpha are going to depend on A, and the coefficient of beta are going to depend on B. And then we are going to build our central map, which is simple. It's going to be simple, a quadratic map given by this multiplication over here and this multiplication over here. This is going to be a map from fq to the n to fq to the 2n. Now our public key in the basic version of extension field cancellation is just the composition of these three maps where t and u are linear maps. U is going from fq to the n to fq to the n, and t is going from fq to 2n to x to fq to 2n. Our private key are gonna be the linear maps. The matrices containing linear forms and the two linear maps T and U. The encryption is pretty standard. We just need to compute our message. If we are gonna encrypt a message and we just compute our public key P applied to our message. And for decryption, we use this formula over here, given a cipher text D1 and D2. What we are gonna do is just solve this system of any linear equation to find the original message. As it is in here, the basic version of extension field cancellation have a lot of problems. One of them is the decryption formula that allows to an attacker to perform a linearization attack if you have enough uh, ciphertext. You can find the coefficient of the matrices beta and alpha and allow and be able to decrypt any other message. It also have weakness because the rank of the central map is low. The rank is 2, and that allows also that the direct attack trying to invert the public key, trying to find pre-image of the public key to be very quick. So to bootstrap the security of this scheme, the authors propose certain modifiers in order to make the scheme more secure. One of them is the minus modifier that is pretty simple. You just need to remove some equations from the original one. So it is parameterized with a parameter A, and this parameter says how many equations we gotta remove at the end. Another modifier they apply is over the matrices A and B, and it is called the projection modifier. And what it is looking for is that the matrices A and B, they want them to have rank n minus 1. And one last modifier, which is called the Frobenius tail modifier, that you can apply that over characteristic 3 or over characteristic 2. In this case, over characteristic 2, you just replace your central map by this equation. This is a map who goes from the big field to the big field, and this is the Frobenius tail modifier. Okay. Besides of the modifiers, the public key in extension field cancellation still have like a rank property. When the minus modifier is applied, and also when it is applied together with the projection modifier, the public key and extension field cancellation satisfy this formula with very high probability, where P1 to P2 n minus 1 are the matrices, the symmetric matrices representing the public key. Here, RA tilde is this matrix over here. I'm going to explain a little bit what this matrix is later. And the matrices G and G prime are just matrices depending of the linear map U and the central polynomial F1 and F2. In this J over here just mean that it is not just simple the polynomial F1 and F2, but the matrix representing the jth Frobenius power of the central map. So you have this equation over here with high probability. You have a matrix like this, where here the I n minus a1 is the identity matrix of this size, and this one as well. This 0 represent a matrix of zeros of this size, and C and D represent matrices over the big field. So if you analyze with detail this equation over here, you get with the conclusion that there exists coefficient over the big field that when you take this linear combination, you have this matrix over here. You also notice that the Frobenius power is just up to A1 and up to A2, where A1 and A2 are just kind of A over 2, roughly. And because of the shape of the polynomial, because of the shape of this matrix, you have that the rank of this combination of matrices here, it shouldn't be big. And also you gotta consider that the matrix W is an invertible matrix. So analyzing this equation over here, you get with the following two results. One of them is saying, if you have a public key in the extension field cancellation when the projection modifier and the minus modifier are applied, then you can find a linear combination of the public matrices such that the rank of the linear combination is always less than this number, a plus 1 over 2, the scaling of that, and then multiplying by 2. And also you can say a little bit more. When A is even, you're gonna only find one linear combination, but two linear combinations that are linearly independent. This is a weakness. This is a way to distinguish an extension field cancellation from a random matrix. I mean, this is a way to distinguish an extension field cancellation public key from a random user matrices of the same size. So you can distinguish that. And this is the main hole that allows us to perform a rank attack. Uh, so the way how we start the attack is by solving an instance of a problem called the Minrank problem. And the Minrank problem is just this problem. You are given a set of n matrices and an integer r, and what you gotta do is to find coefficients such that the linear combination is such that the rank of this linear combination is less than r. So if we look back, what is saying this theorem is that there's the matrices representing the public key in extension field cancellation have a solution for the Minrank problem associated with this r, for this r. So there are the three more efficient methods for solving this problem. We are going to show them here. One of them is the minor modeling of this problem. This establishes the following. It says that if this matrix has rank less than r, then all the minors of size r plus 1 should be 0. So this modeling here leads to a system of a bunch of polynomials of degree r plus 1 in the x variables. Another method for solving the Minrank problem is called the Kniss and Shamir modeling. It is established the following. If you have this matrix over here and you compute the kernel matrix, which is going to be a matrix with n minus r columns, then the multiplication of these two are going to be 0, and that leads to a system of polynomial equation of degree 2 that are also a bilinear system of equations. And finally, there's a new method called support minors modeling, and it says the following. Since this matrix has rank R, then you can decompose this matrix by the multiplication of other two, a matrix S of size n times R, and a matrix C of size R times n. And then you can also say that all the minors of this matrix over here are going to be 0, where Ri is just any row of the matrix given by this linear combination. And this is another new method for solving the Minrank problem. Okay, in our recovery step, what we want to do is this is a key recovery attack. What we should do is just given a public key, we gotta find a bunch of maps such that this composition over here is equal to our public matrix. We gotta find a map P prime, U prime, and two central maps giving us the public key. And hopefully we wanna to find such a central maps that are easy to invert. So the first step in our attack is just solve an instance of the Minrank problem with this target rank over here. This 2 is supposed to be outside of the ceiling map, Anyway, this is gonna be our step, the first step in our attack. And after that, after we find the solution of the mid-rank problem, we build the low rank matrix L1. It is supposed to be a matrix having this rank. And for this matrix L1, we expect to guarantee the existence of a matrix W having this form such that this multiplication over here is giving us a matrix with this form, like with this tail form, where the number of rows that are not zero, like completely not zero, is of size roughly uh, a over 2. And then after we find the solution of the Minrank problem and the matrix W, okay, sorry, the matrix W is like you have a column of elements over the big field, and the second column is the first column raised to the q power, and the third column is the first column raised to the q square power, and so on until the last column is going to be the first column raised to q to the n minus 1. And the way to do that is by solving, we can find this W very efficient by solving a linear system. This linear system over here, where the matrix K is just a matrix representing the rank of the found matrix L1, which is half rank less than this number. So to solve that system, we gotta solve a system of R over 2 times n minus r equation in n variables. And we are not gonna have, we won't have problem by solving this system as long as r is bigger than 2. So that is like an easy step of the attack to find w when r is less than 2, which is by the way the most interesting cases. So we don't have the problem, but we were interested also in find a solution when r is equal to 2. And here is where we introduce this method called subfield spectral decomposition. And what's the problem here? The problem here is the following. You have a matrix F that have this shape. It's just like one column that is not zero, which is sorry, you have one row that is not zero, which is the first row, and you have one column that is not zero, that is the first row. And what you gotta do is you know that F exists, and you have L, you are given a matrix L that is equal to W times F times W transpose, where W is again a matrix like in the previous form. Like you have the first column and the second column is the first column raised to the Q, and the third column is the second column raised to the Q, and so on. And the problem here is to find a matrix W such that the multiplication of, sorry, the problem here is to find a matrix U such that the multiplication of U inverse times L times U inverse transpose result in a matrix having the same shape of F. How we solve this problem? That spectral decomposition. And to see why spectral decomposition works, we gotta see first that to solve this problem, the only thing that we need to do is to find an element U that belongs, that is not equal to, but belongs to the vector space generated by the first column of the matrix W. If we do that, we are able to solve the problem because we take U in this form, and this U is going to be a solution to our given problem. And to do that, to find such a vector here, we just need to do what we just need to do is to find a vector that is orthogonal to our vector w, because if that happens, then the multiplication of L times or multiplication of V times L is gonna be an element in the space generated by W, but also we we have that the multiplication of V times L times V is gonna be equal to 0. So this is a double implication over here. So based on that, we have the following. So what we have here is that we gotta find a vector that is not in the kernel of L and also satisfy this equation. If we have a vector satisfying this equation and that is a vector that is not in the kernel of L, we find a solution to our problem by following step 2. So, and the way to find a solution of this problem is by finding the spectral decomposition of our map L. So first of all, we gotta find 2 ng vectors of our map. That is not always happen, but if we are given a map L that don't have 2 ng vector, we just use a random matrix L and we compute this product over here and we try again to find 2 ng vectors. Once we find 2 ng vectors, we solve this equation over here. That is an equation in only one variable, and we can see that a solution of this equation is given by this formula. And that's it. That's how we find a solution of this problem, a solution of this equation over here, and then we build our solution to this equation, to equation 3. And then by step 2 of and then by step 1 of previous slide, we compute a solution to our problem. And then we take this matrix as the W for the step of the Minrank attack. So after we solve our Minrank problem and find the matrix W, we gotta find another solution to a Minrank problem with the same matrices and the same target rank, but this second Minrank problem is easier because we already have like the matrix in the shape we wanted. But anyway, we are able to find 2 central maps having this form, but this is not useful at all because this map could be really hard to invert. So the last step in our attacks is to find maps like F1 and F2 such that they satisfy this equation over here. Why would we want that? Okay, well, because if we have maps like this, we can invert our central map just as a legitimate user. So we gotta solve this equation, and for doing that, we establish the following system of non-linear equations. So here we know F1 prime and F2 prime that are the maps that we recover by finding the matrix W. And we have one variable for one of these coefficients and one variable for each non-zero entry of the matrices F1 and F2. And that results in a system of this number of equations in this variable. And the system is nonlinear. You have power of Q in here. So it's not a linear system, and we don't know the complexity of solving that system, but we experimentally solve such a system for the proposed parameters in the original paper of extension field cancellation, and the resolution of that system was really fast. So by doing that, by solving such a system, what we are gonna find is four maps, four linear maps of this form. These are linear maps in the big field, so that our first found central polynomials can be written like this. So this is gonna be the composition or of two maps, f tilde 1 and f tilde 2, that are easy to invert, composed by a linear map. So this is our last step, so that our public key and our record polynomial are gonna look like this. We just we not only found P1 and P prime and U prime in our central map, but also a linear map given like this. So the complexity of this attack can be divided in two steps. One step is the first resolution of the Minrank problem, that when we gotta solve a nonlinear system of equation, and the last step when we also need to solve a linear system of equations. For the first case, we kind of understand the complexity of solving Minrank problem, and here we use the keys complexity in the paper we proposed to PQCrypto. But then we realized, because this method was after we published our paper, we can also use support minors for this in this case, and we get better complexity by using support minors. In the second nonlinear system, we don't know the complexity of that, but as I told you, for the proposed parameter in the original paper of extension field cancellation, we solved the system in just few minutes, like 12, 15 minutes. It's no big deal. But in the case of the Minrank problem, we in the paper we estimate that complexity to the 73 by using the Kimnis-Shamir method. But then another method for solving the Minrank problem came up, and that method called support minors uh, says that you can solve the Minrank problem for these parameters in only 2 to the 64, in a complexity of 2 to the 64. And also we estimate in our paper what would be the parameters for getting 128 of bit of security for this scheme. And we wrote, okay, that because we didn't know for minors at that time, we said that for getting this level of security, we gotta take a equals 12 and n equals 249. So we get this complexity for keys. But then when you use support minors, you get 2 to the 100. No, you get 2 to the 100. Yeah, complexity. So that says we gotta increase a little bit more our parameters to get 128 bit of security for the for extension field cancellation. And that's it. That's my talk. I hope you're enjoying this conference so far. So bye.